All right, good morning, good afternoon, or good evening, depending on when you're watching this functions. In this video, we are going to talk about solving system of equations using inverses, and in that process, we're also going to talk about Cramer's rule, which involves solutions to a system of equations using determinants, and also, with that said, if we want to solve a system of three equations with three variables, we're going to need to know the determinant for a 3x3 matrix, so we're going to look at that as well. So let's go ahead and get started. Solving system of equations using inverses rather than the several other ways we have been solving them. So I want to look at the system of equations 3x plus 4y is equal to -2. Sorry about that. And 5x plus 3y is equal to 4. All right, so normally we could solve this using, I don't know, elimination. We could add the two equations together. We could manipulate them somehow. We could do many different ways to solve this equation. But what I want to look at is I want to use matrix multiplication. So this system of equations can be converted into a equivalent matrix equation. And that's going to look like 3, 4, 5, 3. Cool. We call this the coefficient matrix. And then we have x times, the column vector x, y. And if you think about it real quick, this will produce these two expressions. 3 times x plus 4 times y, that's the first equation. And 5 times x and 3 times y, that's the second one. And we want this to be equal to our solution vector, -2, 4. Cool. All right, these are in fact the same thing. So I'm going to go ahead and call my coefficient matrix A. I'm going to go ahead and call my column vector here, x, y. I'm going to call that capital X. And I'm going to go ahead and call my solution matrix, my solution vector here, B. So we have the equation AX equals B. And I want to solve this for X. And if you think back to algebra, you might be tempted to divide by A on both sides to eliminate the A. But with matrix with matrix operations, we don't really have a division operation. But if you think about like this equation, you didn't really divide by 5 when you were in, I don't know, 4th grade, 3rd grade, whatever. You multiplied by the inverse with respect to multiplication. 1 over 5 times 5, that's 1, the identity element with multiplication. So this would have been x is equal to 3. So we're going to do the same thing up here. But what's interesting to note is with this equation down here, we multiplied on the left side on the left-hand side of the equation, and we multiplied on the right side of the right-hand side of the equation. And this will not work with a matrix equation because multiplication is commutative when we are talking about the algebra that we've done, but multiplication is not commutative with matrix multiplication. So if I multiply on the left-hand side over here, I have to multiply on the left-hand side over here. Let's call it left apply. Right? You can right apply also, but left apply. But whatever you do on the left-hand side, you also need to do on the left-hand side on the other side of the equation. So if I have this first, matrix multiplication is associative, so I can go ahead and write this as that. And then A inverse times A, that's just the identity matrix. And we're left with our solution. X is going to be A inverse times B. So let's go ahead and do that with what we have over here. So I'm going to go ahead and grab that. So in order to proceed, we need to know what the inverse of A is. Let's go ahead and figure out what that is. So this is A, this is X, this is B. A inverse is going to be, or we're going to take A and D and switch them. Oh, that doesn't do much. And we're going to go ahead and make B and C their opposite. Right, that is not the inverse because we also need to multiply by the determinant 1 over AD minus BC. AD is going to be 9, BC is going to be 20. So we have, what is that, 1 over negative 11. So A inverse at the end of the day is going to be, I'm just going to write it on the outside, negative 1/11 times 3, negative 4, negative 5, 3. Cool. And then our solution, X, is going to be that thing times negative 2, 4. So let's just go ahead and figure out what that's going to be. So we got 3 times negative 2, negative 6. That's going to be plus negative 16, so negative 22 divided by negative 11. That's 2. And then negative 5 times negative 2, that's 10, plus 12, 22, that's going to be negative 2. So there's our solution, 2, negative 2. All right, so with all of that said, we now have a plethora of ways to solve a system of equations. We have substitution. I like to call it the algebra 1 way or the algebra 2 way. We have method of linear combinations. All right, that's where you take one equation, you multiply it by some constant, you add it to the other one, and you try to eliminate variables. We have the new ones. We have Gaussian elimination, which is arguably the fastest if you have a computer on your side. And we have our newest one. We have converting to. Let me go ahead and write this actually legibly. Converting to a matrix equation. Alright, so you got to pick whichever one you want, and it kind of just depends on the scenario which one's going to be the most efficient or make the most sense. Alright, with that stated though, let's go ahead and kind of expand on this final method of converting to matrix multiplications. What I want you guys to do right now is I want you to solve this system of equations using matrix equations. That's an E right there. And then Cx plus dy equals f. So go ahead and take a second to solve ax plus by equals e and cx plus dy equals f. In other words, solve every single possible system of two equations with two variables. All right, I'll see you on the other side. Here I go. Convert this thing to a matrix equation. Got my coefficient matrix. I have my column vector for my solution. All right, cool. I'm going to go ahead and multiply the left-hand side by the inverse of this matrix right here. All right, I'm going to multiply this by A inverse. I'm going to multiply the right-hand side also by A inverse. So let's go ahead and figure out what A inverse is. A inverse is what we derived in the last video lesson. So we got D, A, negative B, negative C, all times 1 over AD minus BC. I can multiply on the right-hand side because it's a constant. Cool. All right, so I'm going to go ahead and I'm going to have XY is going to be equal to that thing. Times EF. Cool. All right, I'm going to take that to the next page and go ahead and expand that thing. All right, so I have expanded the solution set to all systems of equations. All right, there we are. That is the solution to all systems of equations. So this is the solution to ax plus by equals e, cx plus dy equals f. This is the solutions for x and y. So if you're unlike me, you could probably just memorize this and always know the solutions to a system of two equations. But if you are like me and you don't feel like memorizing that, we can try to interpret our solution here. So the first thing I want to point out is the denominator of the solution to any system of equations of two variables. The denominator is the determinant. So we know the determinant already as the thing that tells us if a matrix is invertible. So like, what is a determinant? Right? One thing is that it tells us if a matrix is invertible. But what I want to point out here is that the determinant is also the denominator of the solution set. Right, it is also the denominator of the solutions to a system of equations. So let's go ahead and keep that in our brain. Let's look at the DE minus BF and the AF minus CE. What do those mean? Actually, before I move on, I do want to talk about what if the determinant is 0? What does that mean in terms of a system of equations? If the denominator is 0, what does that mean? Your first thought, and go ahead and think about what that means. But your first thought might be to say that there are no solutions. Right? If the determinant is 0, there are no solutions, which would be partially correct. There are actually two scenarios. This might be the case, there are no solutions, but it might also be the case that there are infinite solutions. Right? Or infinite solutions. Right, here are two examples that kind of show that. So example number 1, think about the system of equations 3x plus 4y and 6x plus 8y. Let's go ahead and set those equal to like 5 and 7. Right? The determinant here of the coefficient matrix is 0. It's going to be 3 times 8, 24, minus 6 times 4, 24. So AD minus BC is going to be 24 minus 24, which is 0. And that's telling us that something weird is going on. And if you solve this by another method, you're going to see that there are no solutions here. Right? No solutions to my example number 1. But I could just as well look at the equation 3x plus 4y and 6x plus 8y and set those equal to things that are also parallel. So 3, 6, 4, 8, let's go ahead and say 2, 4. This thing, the determinant is 0. The determinant of my coefficient matrix is 0. But there are infinite solutions. So just keep that in mind. AD minus BC, all right, if you're memorizing this thing for some silly reason and you are quick to think that there are no solutions, there might actually be an infinite number of solutions in this example over here. All right, but back to what I was saying before about the numerator, right? The denominator, the determinant, is the denominator of our solutions to a system of equations. But what about that numerator? So let's inspect that thing. All right, so this numerator also kind of looks like a determinant, and there are many matrices that we could write that would have determinant DE minus BF, but if I'm clever and I write it like this, we got E, F, and then BD. This has the property that the right-hand side of our initial system of equations, where is that thing? Right here. The left-hand side, I keep saying that, right-hand side of our system of equations has replaced the x coefficients of our system of equations. So we have the original ABCD coefficient matrix, and we have replaced the x entries with the right-hand side, EF, BD. Likewise, in the denominator, we have the matrix with determinant AFCE. We can go ahead and write EF, and we can write AC here. I believe that's going to have the correct determinant, this thing right here. We have A times F, good, minus CE, good, and this is the coefficient matrix. Let me go ahead and do that. This is the coefficient matrix, A, B, C, E. A, B, C, D, with the y entries replaced by the right-hand side of the equation, A, C, E, F. So what does this say? All right, so I'm going to go to the next page and just kind of start over. So we have the system of equations AX plus BY equals E. We have CX plus DY equals F, and the solutions to this system of equations were x is equal to, the denominator is the determinant of the coefficient matrix. The numerator for x was DE minus BF. Okay. Down here for y, we had the exact same thing, the denominator, AD minus BC. Right, this is for all system of equations. The denominator is the determinant of the coefficient matrix. The numerator for y is AF minus CE. And the notation for determinant is just two vertical bars, like absolute value. Inside of it, the inputs to the matrix, so A, B, C, D. Right? But the numerator for the solutions for x, we're going to replace the x column with the right-hand side of the equation, and we're going to leave the y column alone. And down here, we're going to, for the y solution, replace the y column with the right-hand side of the equation, leave the left-hand side alone. And this is a nice, easy way to remember the solution to a system of equations. Right? The denominator is going to be the determinant, and the numerator for the respective variable is going to be replace that column, so the x column, with the right-hand side. For the y, replace the y column with the right-hand side, leave everything alone. This might seem a little convoluted, but as we enter larger dimensions, as we enter 3 by 3 systems of equations, 4 by 4, 5 by 5, this process is still going to work. And this process has a name. The process is called Cramer's rule. All right, so Cramer's rule is x equals the determinant of replace x with EF all over the determinant of the coefficient matrix in general, and y is the determinant of replace y with EF I'm being a little bit redundant here, but I think that's good. Really drill it in. A, B, C, D. All right, cool. So this is Cramer's rule. This is a way to solve system of equations. So we can go ahead and add that also to our long list that I have way here at the beginning. Where is it? Right here, yeah. So let me go ahead and write 5. Cramer's rule. Thanks, Kramer, for that rule. All right, so the last thing I want to do in this video is talk about Cramer's rule for 3 by 3 matrices, or 3 systems of equations with 3 variables, 3 equations, 3 variables. All right. All right, so we are going to have the following system of equations: ax plus by plus cz dx plus ey plus fz, and then gx plus hy plus iz is going to be equal to j, k, and l. What are the solutions to this system of equations? So if we use Cramer's rule says it's going to be the determinant of, so we have this coefficients matrix A, B, C, D, E, F, G, H, I, and we're going to replace, for x, we're going to replace the x column with J, K, L. So we're going to have J, K, L, and then we're going to have B, C, D, E, F, G, H, I. That's the numerator. The denominator is going to be the determinant of the coefficient matrix in general. So A, B, C, D, E, F, G, H, I. Cool. And that's the solution for x. Y, we are going to have, we're going to replace the y column with J, K, L, and then the rest will be A, B, C, D, E, F, G, I, and then the denominator is going to be, once again, the determinant of the coefficient matrix, A, B, C, D, E, F, G, H, I, and then Z. The solution to Z is going to be, we're going to replace the Z column with J, K, L, and then we're going to have A, B, D, E, F, G, H, and then down here, A, B, C, D, E, F, G, H, I. Cool. All right, so that is our solution to this system of equations using Cramer's rule. Now the real question is, how do I evaluate the determinant of a 3 by 3 matrix? So let's do that. Here is the process. The determinant of a 3 by 3 matrix. So I'm not going to get into the why here, so you're just going to have to just go along with what I do here. But the first thing I need to do is, well, you know what, let's give ourselves an example to actually compute, really feel this thing out. I want to determine the determinant of this matrix here, or this array of numbers. So the first thing I need to do is I need to define some words. So I'm going to define the word minor. A minor is the row I, column J minor. So there's 9 minors in this matrix here. The row I, so like row 2, column 3. So the -2 minor is, let me go back though, the row I, column J minor is the determinant of the matrix that results from deleting the ith row and jth column. And I just have enough room for that definition. So the minor of a matrix, though there are 9 minors, there's going to be a minor for each number, for each position. The row I, column jth minor is the determinant of the matrix that results from deleting the ith row and jth column. So let's say I want to determine the 2, 3th minor. So I'm looking at the number -2 here. I'm going to delete the 3rd column. I'm going to delete the 2nd row, and I'm left with something that I do know how to compute the determinant of. 2, -1, 1, 6. So 2, -1, 1, 6, that's going to be 12 minus -1 plus 1, that's going to be 13. So the minor, the what do we write is the 2, 3 minor here is 13. All right, this process is a little bit strenuous. Let's keep going. All right, I have another definition for you. So we have minor, and now I want to define what a cofactor is. We're building up towards this, how to compute a 3x3 matrix determinant. So a cofactor is a signed minor. All right, let me explain what that means. So let me go ahead and rewrite my matrix that I previously had. We have 2, -1, 4, 0, 5, -2, and 1, 6, 3. All right, we're looking at the determinant of this thing. So a minor is you're going to delete the row and the column, and then the matrix that's left behind, you're going to take the determinant of that thing. A signed minor is as followed. So C ij is going to be the minor ij, but we're going to multiply by -1 to the I plus j. Right, so what does that become for, let's say, C23, the one we had before? So C23, that was 13, but that's going to be -1 to the 2 plus 3. So the cofactor, the signed minor here for this spot is going to be -13, -1 to the 5th, -13. So if you look at where you are in the matrix, if you have 2 plus 3 here, we are at 2, 3. If this sums to an odd number, this -1 is going to stay -1. If it sums to an even, it's going to become a 1. So one nice way to remember what the sign of your cofactor is going to be, or whatever this -1 is going to become, is where it is in its position in the matrix. So if I have some arbitrarily sized matrix, A1, 1, A1, 2, A1, 3, ... and then I have like A2, 1, A2, A3, 1, ... and I have this matrix here. What's going to happen is 1 plus 1, that's going to be 2, so that cofactor is -1 to the 1 plus 1, that's going to be a positive number. And then 1 plus 2, that's odd, that's going to be negative. 1 plus 3, that's going to be positive. So we're going to alternate back and forth. And same thing down here, 2 plus 1, that's odd, so that's going to be negative, positive. This thing's going to be positive right here. It's going to be 2 plus 2. So it alternates back and forth. We have this checkered pattern. All right. And so knowing where you are in the matrix, sometimes you can just know whether or not that's going to be a plus or minus. Nice little trick. All right, so back to the task at hand. We are going to take the determinant of this matrix right here. And what you need to do is as follows. You want to expand along any row or column. All right, if we were in class right now, what I'd have everyone do is pick a row or a column that they want to do this, and then we will all get the same answer. But for the purposes of that explanation, I'm going to go along row 3. So what does that mean? All right, so the determinant of a matrix is going to be A1. This is going to be equal to A31 times the cofactor 31 plus A32 times the cofactor 32 plus A33 times the cofactor of 3. So we're going to do this in 1 second, but once again, you could do this for any row or any column. A31 is 1. What is C31? Well, we need to know the SIGN of it, the sign of it. So it's going to be -1 to the 3 plus 1. That's 4. Or you could just remember that this is a plus, this is a minus, and then this is a plus. That's what I usually do. But right now I'm just using this. Where is it? Definition right over here. So back to here. And then what is the determinant of the matrix left over when I eliminate column 1 and row 3? That's going to be 2 minus 20, which is going to be -18. Awesome. Cool. All right, A32. Let me go ahead and actually back up real quick. Get rid of those crisscrosses. All right, A32, that's going to be this element right here. That is 6, and then its SIGN is going to be a -1, a -1 to the 5, and then the determinant left over, if I get rid of this column and this row, that's a -4 minus a 0, which is -4. And last but not least, A33, that's 3. It's going to be -1 to the 6th. And if I get rid of this row, this row and this column, I get 10 minus 0, which is 10. All right, let's go ahead and finish this thing up. 1 times -1 to the 4th times -18, that's just -18. 6 times -1 to the 5th times -4, that's going to be, what is that? That's going to be a plus 24. And then over here we have 3 times -1 to the 6th times 10, that's a positive 30. And then we have a -6 here. A positive 6 and a 30, that's 36. There is our answer. The determinant of a 2, -1, 4, 0, 5, -2, 1, 6, 3 matrix is 36. And you could have done this along any row or column. All of them would have given you 36. You know, I'm going to do it one more time real quick using column 1 because they got that 0 here. That might be nice. So let's see, we got 2. -1, 4, 0, 5, -2, 1, 6, 3. All right, we're trying to determine the determinant. And I'm going to expand along column 2. Sorry for that terrible circle. Column 2. So let's see, we got 2. And then the cofactor 2 is going to be, it's going to be 1 plus 1, which is going to be positive 1. And then we are going to go ahead and look at 5 times 3 is 15 minus -12. So 15 plus 12 is 27. Cool. You'll notice that it's always going to alternate because of that checkered pattern. So, I'm just going to throw a negative right there and not even worry about the -1 to the 3. So we have a -0. That is nice. That's just going to get rid of this whole thing. I could stop right now if I wanted to. I'm not going to. But we have -1 times 3. That's -3 minus 24. -3 minus 24 is -27. But that's just going to go away because of that 0. And then the last thing, we have a plus. I'm not going to worry about the plus or minuses because it's alternating. we have, we're looking at the 1, so we're left over with, well, let's not forget the 1, even though it's not super important because it's 1. 2 minus 20 is going to be negative 18, so hopefully this is going to work out in our favor. We have, what is that, 54 minus 0 minus 18, and 54 minus 18 is 36. Beautiful. B-E-A-beautiful. Alright, so I got one last problem for you guys, and I'm actually not going to do it for you. I want you guys to do it. So I want you to find the determinant of 3, 2, 7, negative 4, 0, 1, negative 2, 0, 5, and then 0, 4, 1, 6, 3, negative 3, 1. Gotcha. I want you to find the determinant of this 4x4 matrix. Torturous? Maybe, if you were to expand along row 1, but there is a sneaky way to do this problem, so I'm going to leave it for you guys to determine the determinant. Oh, and also one thing you can do if you want to is show that this process, expanding along rows and columns using cofactors, also works for 2x2. That's up to you. Alright, so what did we do in this video? We did a lot of things. We solved a system of equations using inverses, and then we established Kramer's rule, a new way to solve system of equations. So we got 2 new ways. And then we looked at how to find the determinant of a 3x3 matrix, a long and grueling process. It did not justify it, but just trust me on this one for now. There are some algorithms out there that you can use as well. The textbook has them pretty straightforward, but use what you want to determine the 3x3. But yeah, there is solving with inverses. Have a awesome Monday.